Alrighty, chapter 13. Holy man, chapter 13, lesson 6. We're going to be on to lenses. So there are two types of lenses that we're going to learn about. You need to learn both terminologies, okay? So we have a concave lens, which is also known as a diverging lens. All right. So just keep that in mind. Concave lens is a diverging lens, okay? Concave mirror is converging. The reason that's called diverging lens is because it makes the rays diverge, as in go away from each other. So concave mirror converges, concave lens diverges, convex mirror diverges, right? And convex lens converges. And this is where we have a convex lens. Okay, now these are what's called double converging and double diverging and double converging lenses. See how it's on both sides, it's concave on both sides, and this is convex on both sides. You're only going to deal with double in this. So everything we learn is really only for these two types. So you have basically four things you're learning about. You have a concave mirror, concave lens, convex mirror, convex lens. But you have to know when the converging, if they say converging mirror, you have to know that that's concave. If they say diverging mirror, you have to know that's convex, right? I say they, it's like you're writing a diploma. You're not going to be writing a diploma. But when I give you tests and score, you're doing your practice problems, this is kind of terminology you need to know, right? So lenses is basically based on the principles of reflection. Okay, it enters glass and it exits glass. As it goes through, you're basically going to have some different things. Okay, so what's going to happen is, and I usually show you guys this in an actual lab, but we can't have that happen. It's really cool. You can send 3 different beams of light, and they'll diverge, and when they meet in the middle, they actually show up as white, which is pretty cool. But what you should notice is that since the light travels through the lens, we're actually going to have a focal point on both sides. So for this mirror, there's a principal focal point here. There's technically also, or not mirror, sorry, this lens, there's a principal focal point here. There's also one over here. And same as this lens, there's a principal focal point, which is over here, and a secondary one over here. And so there's focal points on both sides. Remember, the light is always going to travel through, okay? It's refracted. So remember, it's going to be traveling through, okay? Whoa, we're skipping pages. So mirrors similar lenses, but also different. So the similarities, notation, convex, concave. The formulas we use are exactly the same. And DO is still always positive, right? And values are real when they're positive and negative when they're virtual. That's the same. All right. C equals 2F no longer applies. The material of the lens affects the distance of the focal length. Okay, so it doesn't, the C equals 2F does not apply as far as it goes for lenses, okay? Real is actually on the opposite side of the lens, so that's what is really happening. The virtual is on the same side as the object. And so now our positives and negatives change depending on what we're talking about, right? So let's put this pen on, right? So let's say we just have, it doesn't matter what kind of lens we have, either one. Okay, our DO is positive always. It's always positive. But now this side of the lens is negative and this side of the lens is positive because we expect the light to travel through, right? To travel through and create images on this side. Or if it's a concave lens, right? The images will travel through, but they'll create a virtual image by us backtracking these things, okay? So create virtual images, all right? So there are different types of characteristics, right? But the same idea. We still have size, larger, smaller, same, orientation, upright, inverted, or type, real or virtual, okay? Real images can be reflected on the screen, right? The light rays themselves actually converge to that point. And real images for lenses are always inverted. Okay, virtual images cannot be projected onto a screen. You guys have all done Bio 30, so you should have, I don't remember if it's still in there, but you're talking about light. When a picture actually hits the back of your eyeball, right, when you have your eyeball here, okay, it's a nice eye. When you have an image and it goes through, basically what's a lens, it's actually going to give you a upside down version of that image on the back of your eye. Your brain just reorientates it when it realizes it takes that stuff in. So just keep that in mind. Virtual images cannot be projected on the screens. You must look through the lens to see a virtual image. So just like you must always look in the mirror to see a virtual image. Okay, so that's kind of the concept there between virtual and real images. Okay, all right. double concave or diverging lens. Okay, so we're going to call them concave or diverging lens. All right, so keep that in mind. Okay, they're synonyms for each other. Okay, so very similar idea. If we send in one parallel, it's going to act as if it came from the focal point. If we send one through or towards the secondary focal point, it'll end up going parallel. And if we send one through the vertex, it'll just go straight through. So keep that in mind. Through the vertex is straight through, and if we send it parallel, it looks like it came from the focal length. Notice how the rules are all kind of similar, but remember for lenses, they're always going to go through. Now we do have to backtrack in this case, right? And so here we go. We have this one here. Use a ray diagram to draw the image produced by the lens. State the characteristics of the image. So I'm just going to use the two rules. The first rule being if I send one in parallel, it will diverge. Okay, this is why we have to know the difference between lenses, because we have to know if it's going to go this way towards this focal point or away. Okay, that's the difference between diverging and converging. Notice how these rays are actually getting farther apart once they pass through the lens. That's hence the diverging. All right, and so this one goes off this way. Then we can send one directly through this. Now, if we were to backtrack the yellow one, it would still end up looking along that line. So what we have here is these two meet here. So that's going to create our image. Well, what kind of image do we have? Well, first of all, the image is virtual. The image is virtual because of the fact that we have to actually, these two solid lines don't meet there. We have to backtrack them, right? I couldn't put a piece of paper there and see that blue line. That blue line never actually hits a piece of paper. It's just when we observe something from over here, it appears as if it came from that position, right? So that we have a virtual image. It's upright and it's smaller. I'm just gonna, okay, that's supposed to be a little eye below the line, so don't get confused with what the eye is. Yeah, there's a little eye there below the line. Why don't I just erase that, rewrite it, so you guys can see what I'm talking about. Okay, this is the image. All right, so smaller, virtual, and upright. Okay, and again, we can do the dimensions, but that just is based off of us going through it. Okay. All right, so concave lenses, images are always the same. Okay, they're upright, smaller than the object, and virtual. There's nothing else we can do. So upright, smaller, and virtual. That's generally it. It's going to look like that. Okay. Yeah, it's similar to the images formed by convex or concave mirrors, and it's kind of vice versa, right? Convex lenses are similar to concave mirrors, and concave lenses are similar to convex mirrors. So that's where we're going to get confusion. This vocabulary is going to get you confused as to what's going on, but you have to just remember your rules. Mirrors reflect, lenses the light passes through. Then you have to know what converging and diverging is. What happens? Where do they converge? Where do they diverge? Okay, and kind of be able to do that. All right, so that is the double concave. Now we're going to talk about a double convex. All right, and we're not going to deal with single convex or single concave as far as questions go. All right, so first thing we have is the same idea. We send in, zoom in here. Okay. If we send a ray in parallel, it's going to go through the focal point. Notice that this side is now the principal focal point. This is the secondary one. If we send a second one through the vertex, it's going to keep going. And if we send one through the secondary focal point, it'll then go parallel. All three of these converge here, which means we're going to have a real inverted image in this case, right? All right, give this a try, see if it'll pull up. It probably won't because it's a Flash player that's probably not installed on a computer, but you can use it and move it around, and you'll see that it kind of does a lot of interesting things. Okay, all right, so we're going to use the ray diagram to complete this here. All right, so what we're going to do here is first the blue line goes in parallel, and then it's going to go through the second focal, or the principal focal point. Then we have one that goes through the vertex, and it's going to pass right through. If I wanted to draw a third one here, I could technically, it's going to not be perfect, but I'm going to draw it through here. Let's go through the focal point, and then it's going to go parallel, right? And so what you'll see is they kind of all converge there. Now, I have the characteristics here are real. This one's approximately the same size, but it's not exact, and it's inverted. So real, same size, or approximately the same size, and inverted. But it looks like it could be a little bit larger by our diagram. Okay, And so that's kind of the idea. So you can have, but we're just going to use the blue and the yellow law, because remember we only need two, because once we find where those two cross, we're good. All right, so on this one here, what we're going to do is we're going to move basically the object closer than the focal point. So if you look at the last question, the focal point, the object was farther than the focal point. Now we're going to move the object closer. If we move the object closer, what's going to happen is it's going to send one parallel, and then it's going to go through this principal focal point, and then we're going to send one through the vertex, which just continues on straight. And what you'll notice is these blue and yellow lines, they don't go towards each other, right? They're diverging over here. So now we're suddenly so close that they're diverging, which is interesting, right? Because if they're diverging, what's going on? And so it's a converging lens. Crazy, right? But it's because we're so close to the focal point, right? And so we have to backtrack them, and we actually get is a virtual, larger, and upright image. So what's important is that it's virtual because we had to backtrack, right? That these two beams of light never actually hit each other, right? They just appear to come from hitting each other up here, right? And then it's larger because it's taller, and then it's upright, okay? So kind of focus on that. That's, again, this is a better exact diagram of it, but you guys get the idea, okay? So you can do example diagrams using convex lenses. You can memorize these. There's these two rules, and then these three rules, right? It's generally not considered normal practice to memorize it. All right. One thing that's interesting is that if the object is at the focal point, there's no image produced, which is kind of interesting if you have certain things like glasses at a certain distance, if they're convex, which usually they're not, you can kind of do that. Okay. This is a good example. So if you think about, this is what this is Chris Hadfield, right? And where he is he's in space. And so he's got a water droplet, right? A water droplet. And if you think about water droplet, well, it's going to be a ball, essentially, because of the surface tension. And if you think about a ball, well, a ball is essentially a double convex lens, right? And so if you see here, you see that his head is this way, and his head is this way in the image. So in the object, which is him, he's the object, right? So what we're getting is this this real image, right? So we actually could put a screen here, but we're seeing a real image, right? That's being inverted. It's being inverted, and it's smaller because of the fact that we have a lens, right? And this is it's a really good example, right? Okay, and then we can talk about how vision works and different kinds of lenses, right? You can see there's a whole bunch of lenses. These are all different types of lenses they can use that can help correct where the image is and how the image appears in your eyeball. But you'll notice that basically what's going to happen is everyone has a convex lens. Double convex is their main eye, but then they can put glasses in front of it and it can correct things, right? This talks about nearsighted and farsighted. I haven't had glasses, so I don't understand the difference a lot, nearsighted and farsighted, but it's something that you can kind of talk about. Okay. You can do this. This is kind of an interesting little thing. This is not something you have to watch if you're bored of physics for today. This is just interesting as far as like you can look through the peephole, and it's a cool little physics concept. Alrighty, so the formulas still stay the same. All right, one thing though is we have to remember that now the positive side is on the opposite. Okay, here is this object is always real. Okay, the focal length is negative for a diverging lens. Okay, and it's all kind of this concept gets brought back. All right. So here is lens example number 1. So a flower is 1.2 centimeters in diameter, which you're just going to say tall, right? 1.2 centimeters tall, because the diameter is kind of talking about we're going to say tall. Okay. And it's 90 centimeters from a camera's lens, right? And the focal length of the lens has a magnitude of 150 millimeters. Okay, what is the distance between the lens and the film, and how large is the image of the flower? Draw an array diagram to verify the results. So what we're going to do here is we have a height of 1.2 centimeters, right? So that's our height of our object. The distance of our object is 90 centimeters away, and the focal length is 15. All right. So what we have here is this idea that we have our first equation here, which we can put in. Now, the focal length is positive because it has a... Oh, sorry, my dog just walked in. She's bothering me. There we go. She left. Okay. It has a focal length is positive because it is a converging lens. It's a convex lens, right? So keep that in mind, that matters. So we start with our first equation that we have the information for, and we solve the DI is 18. So even though over here is positive, the distance of the image is now positive on this side. Okay, so the DO was originally positive, but that's the only thing that's positive on this side. Everything else on this side is now negative. Okay, everything else is on this side is now negative. All right. Then I can use that and go ahead and go through this, and I'm going to get the height of the object is negative 0.24. So it should be inverted, smaller, and closer, right? It should be inverted, smaller, and closer. And when we do the diagram, right, we get exactly that. It is inverted, it's smaller, and it's closer, right? Now in my blue line, I went in, then through the focal point, right? So in parallel out to the focal point. And my yellow line, I go in through the vertex and out through the vertex. They're going to converge over there. Alrighty. Okay. So here we go. We have this. I'm actually going to draw it out for you guys. So you can kind of follow along with me. An object that is 24 centimeters in front of a diverging lens. So that's our distance. Right. I just wrote 24 down here. All right, and has a focal length of negative 15 centimeters. The reason it says negative is because it's telling you that's a diverging lens. All right, so there's a focal length there. Now there's a secondary focal length also over here at 15. Okay, there's a secondary focal length also here at 15. So what we have here is we have our distance and our object and our focal length. So what are the characteristics of this image from the ray diagram as well as the equation? So if I go ahead and I kind of test this out, what's going to happen is I'm going to send our blue ray through. Our blue ray is all goes parallel. Okay, it just hadn't picked blue as a color. All right, and it's going to act as if it came from this focal point. So it's going to do this. All right, and I'll have my yellow ray, which goes to the vertex. All right, and so when we get those, we're going to get a image here, an image right here. Looks like that. Okay, that's our image. And so what we should have is an image that is closer, smaller, and upright. Okay, it should be closer, smaller, and upright. Now, it didn't give us the height, but we can assume that it's going to be smaller because it's closer, right? And so what we'll do is we will just double check that with our equations here. So 1 over F equals 1 over DO plus 1 over DI. Okay, and so we'll put in 1 over negative 15 equals 1 over 24 plus 1 over DI. When we solve for DI, okay, we're going to get what kind of number? So we'll do 1 over negative 15, subtract 1 over 24, and do 1 divided by that answer. Oh, sorry. 1 over negative 15. Subtract 1 over 24, and what did I do wrong here? Oh yeah, no, that works. Sorry. Yeah, it's going to get negative 9.2, right? So it's going to be negative 9.2, which makes sense, right? Because the image is going to be on the negative side, right? Remember, this is the negative side, and this is the positive side. So the image is on the negative side, and it's closer, right? So since it's closer, we're going to need a smaller image. So we know that this is going to be, as far as image types go, virtual, because we had to backtrack the blue line. Okay, virtual, smaller, and closer, and upright. Okay, so smaller and closer generally go together, right? Same as farther and larger do. Okay, so that's that example. Hopefully it's not too messy for you. You can read it. I'll zoom out on that example as well so you can get that all copied down. All right. So this is how we get pictures in space, right? So a picture of the sun only runs a specific wavelength through but we use lenses in space to allow light to come in, because what's happening is, you think about the sun, right? the sun is sending rays. So here's the sun. The sun is sending rays like this, right? And we're here on Earth, right? And we want to see the sun. We want to see the sun. And so in order to see that, we need to put a lens here that converges the rays back towards us so we can actually see them. Alrighty. So past problems 26 through 29. There is no quiz. You guys are that'll be done at the end of this chapter. And then you can go ahead and do the next chunk. Thank you.